All right, we are ready to move on to the next talk. So I would like to introduce Dr. Patrick Treuthardt.
All right, thank you. So I'm Patrick Treuthardt. I am an astronomer at the North Carolina Museum of Natural Sciences in Raleigh, North Carolina. So if you ever happen to be in that area, please stop by. We have a visible lab space where you can check out researchers at work. Ours is a little different. We have paleontologists. We have, people working on genomics, things like that. We have an astronomy lab, a visible space astronomy lab. It's a little different. Nobody likes watching people code, so what we do is we actually kind of show the products of research. So we have a lot of neat little videos and things like that showing products of research in astronomy. What I'm going to talk about is a couple of citizen science projects that I developed with my friends and colleagues, Ian Hewitt and Alptez Bazarian, about basically looking for black holes in galaxies, looking for specific black holes in galaxies. What I'm going to do is I'm going to give you a little bit of background about galaxies, because I don't know that everybody knows about galaxies as much as I would think they do. Oh, sorry. I'll plug this in. Well, I can skip that. All right. So to start out with, we're going to talk about the Milky Way, because this is the galaxy that I'm sure we're all familiar with. Living out in Idaho, I'm sure people have seen the Milky Way. Everybody's seen the Milky Way? All right, perfect. I grew up in Detroit. I did not see the Milky Way. I didn't see much. I saw Orion and I saw the moon, and that was kind of it, until I went to undergrad in New Mexico, and then I saw everything, which was fantastic. But yeah, so this is the Milky Way. If you're in a really dark area, you could potentially see some color, which you can see here. So right here is the center of the Milky Way. This is the bulge right here. Out here is the rest of the disk of the Milky Way. You can see that the bulge looks a little more yellowish orange, and the disk looks a little more blue. It's because there's a lot of star formation happening out here in the disk area, so you get a lot more blue stars there. And you also see this dark band cutting through here, and that's all the dust in the Milky Way as well. If we look at so we're in the plane of the Milky Way. So if we want to actually look at the Milky Way from top down, we can't actually do that, because the Milky Way is about 100,000 light years across. It's a very, very large object, and there's just no way to get outside the Milky Way. So you have to be creative to kind of figure out what the Milky Way looks like internally. One analogy I've heard is you essentially have to it's like mapping out your neighborhood, only you're stuck in your house, and so you have to kind of map out the streets in your neighborhood, looking out your window, looking through your neighbor's window across the street, and so on, trying to map out what your neighborhood looks like. The Milky Way it's similar, and so this is an artist's rendition of what we think our galaxy looks like. And if you were standing outside of it, so right here is where we are. Right here's the sun, about halfway out to the edge. This is the bulge here. This is that yellow-orange bulge that you see. There's actually a long bar structure right here, and then the arms of the Milky Way are actually coming off the ends of the bar. And so the Milky Way is a spiral galaxy, right? So it has these spiral arms, these clear spiral arms. When we look out into the universe, we see that there are different types of galaxies. There's just really, when we look out into the universe, there are between 200 billion and maybe 2 trillion galaxies. And if we classify them, we see that they really fall into two really major types. They fall into something called elliptical galaxies over here, and then spiral galaxies over here. So Edwin Hubble in the 1920s looked at a bunch of galaxies and kind of figured out that they kind of fall into these two main classification groups. Elliptical galaxies, they're very, there's not a lot of structure to them. They're very kind of like, almost like balls of stars. So if you can imagine holding one in your hand, you just rotate it around, it's gonna look the same no matter how you look at it. Spiral galaxies are gonna have a lot of structure to them, right? You'll look at them edge on, they're gonna be very, very thin objects. So if you imagine like stacking two DVDs on top of each other, that's about the ratio of thickness to diameter of a disk galaxy, of a spiral galaxy. But if you look at it face on, you're going to see a lot of structure. You're going to see arms, you're going to see the bulge, you're going to see bars, you're going to see things like that. And what Hubble found when he was looking at these, so the interesting thing is that you could actually, he found that spiral galaxies can actually be broken up into two major groups, those with bars and those without bars. So you have the barred spirals down here in this tine of this tuning fork, and then you have the non-barred spiral galaxies up here. The other interesting thing is that the wrapping of the arms of these spiral galaxies seems to correspond to how large the bulge is. So in these little drawings here, you can see that the larger bulge corresponds to a more tightly wrapped arm, and the smaller bulge relates to a more open arm. Okay, so this is going to be important going forward. So when we look at galaxies in the local universe, most galaxies are spiral galaxies. Between like 60 and 70% or so of galaxies are really spiral galaxies in the local universe. Okay, so what creates these spiral arms? So our best understanding of how these spiral arms are formed and maintained is a theory known as density wave theory. And what a density, well, and basically we've all kind of experienced a density wave. This is kind of an example of that. When you're driving on a highway, then all of a sudden the traffic slows down for no apparent reason, and it keeps going again, right? What happens there is you actually hit a dense region in the traffic. That's a density wave. So in this video here, you can actually see the density wave travel from the faraway point right here and kind of travel down through the traffic right here. So you have the material, the cars traveling along, but there's a density wave traveling through the material, and it's traveling backwards through the material. And that pretty much happens the same with spiral galaxies. So this guy, Kevin Pluck, he created a very nice, very simple simulation that kind of illustrates that, where you can create a spiral galaxy just by changing orbits, right? So you look at all these particles in these circular orbits. What you do is you just stretch them out into elliptical orbits, and then you rotate the ellipses a little bit, then spiral structure just automatically pops right out. And so you're going to see that here in just a second. And so you get nice spiral arms just pop right out there. And what's happening is nothing is different with these particles. They're just entering dense regions. It almost looks kind of chaotic there, but it enters these dense regions, and where those dense regions are, that's where you get the spiral structure. So if you imagine those particles being gas clouds, being gigantic gas clouds, what'll happen is those gas clouds will just travel around in their orbits. They hit that dense region. These gas clouds are going to collide with each other, and they're going to basically be shocked, kind of compress. You're going to get new stars forming, so you're going to get red stars, you're going to get blue stars, you're going to get all kinds of stars forming in these arms. When you get these blue stars, these are very massive stars that are going to burn very bright and very hot for a short period of time. These red stars are going to be lower mass stars that are going to last for a much longer time, and they're not going to be quite as bright. So what'll happen is you get all types of stars forming in these dense regions. The blue stars are going to outshine the red stars, but then they're going to burn out and just kind of go supernova, form gas clouds again that'll kind of travel around in their orbit. The red stars will kind of continue on, but they'll not be so bright. So when they pass out of the density wave area, you're just not really going to see much brightness there. It's not going to be as bright as the arms themselves. So that's basically how we can see the arm structure in a galaxy. It's these gas clouds basically forming new stars in the arms, and that's the spiral structure that we see, and that's where we can see the density waves. Okay, so going back to our original image. So this is what we see the Milky Way as in visible light. Okay, but now if we look at the Milky Way in X-ray, it looks different. I mean, you still see kind of the structure, but you see something different. And looking at this, can you guys point out something that looks a little different from the other image? Some structure there that's a little subtle. What's that? What do you see? Yeah, the cloud. So these things, right? Oh, is this what you're pointing at? Because this is what I'm pointing at. So we have, so there's like, you see a little bit of structure up here, above and below the disk right here. Yeah, I mean, there's something over here too, but really what I'm pointing at is these things right here. And this is unusual. It doesn't, actually shows up better on my screen. These are something known as the Fermi bubbles. And so these are giant afterglows in the halo region, or basically in the almost intergalactic region, in the rarefied gas that's above our galaxy. There's an afterglow that you can see in the X-ray and that you can see in the gamma ray. Okay, And for a while, it was not known what caused this. And there's still research going on about this, but one idea is that these are actually the remnants of jets. So there's something, so we think, well, based on this, what we think is happening, one theory is that there's a massive object in the center of our galaxy that's creating that created very, very strong jets that shot material at high velocity out of the plane of the galaxy, and it shocked the rarefied gas in the halo of the galaxy, in the outer parts of the galaxy, slammed into it, and then caused it to glow at very high temperatures. And then the jet turned off, and you no longer see it, and you're just seeing the afterglow of that slamming into the external medium. So this is a galaxy, Centaurus A, where you can actually still see these jets, and you can see the shock wave right here where it's slamming into the gas in the external medium. Okay, and so this is an example of a different galaxy where this is actually happening. Okay, so what is the object that's doing this? What can be causing this? Well, if we zoom way in to the Milky Way, if we zoom way into the bulge, into the nucleus, what we should see is a dusty disk. Okay, so we have this dusty disk right here, and then you have these jets kind of shooting out perpendicular to this disk. Okay, and if we look inside the disk, what we'll see, so this is actually a torus, this is more like a donut. So here are the walls of that torus right here, the walls of the donut, but if we look in there, there's going to be a disk of material spiraling around and falling into a very massive object. And the only thing that could create jets that produce this much energy and shoot material out at that speed that can basically slam into this medium is a black hole. Okay? And so what's happening here, or what possibly happened in the past, is that material was falling onto this black hole, and as it spirals into this black hole, it basically heats up, right? So you have, imagine gas traveling on the inside track and gas traveling on the outside track. The material on the inside track moves faster than the material on the outside track, so you get friction, you get basically viscosity, it heats up, it causes it to glow. Eventually it heats up so much that it turns into a plasma, which is basically free-floating particles. You have basically charged particles moving, you get an electric field, or you get a magnetic field. These particles get trapped in the magnetic field and they get shot out at high velocities. And that slams into the medium, and that's what you see. Okay, so this is some evidence for a black hole in the center of our own galaxy. Keep using the clicker. The best evidence we have for a black hole in the center of our galaxy is data that was taken somewhat recently from the Event Horizon Telescope. So this, I'm sure everybody's seen this kind of in the news. This is a picture of that accretion disk, and then that shadow, that dark spot here is actually the shadow of the black hole in the center. It's not the black hole itself, it's just kind of the region around the black hole that's not emitting much light. But the black hole is in there. And so you can see that it's not very big. I mean, relatively speaking, it's about 4.5 million times the mass of the sun, so it's a very massive object. But diameter-wise, it's a very compact object, so it's going to be a black hole. I think the most visually interesting example of this black hole is a series of images that were taken over 20 years, pointing at where the black hole is, and just optical images. And what they did was actually just track the stars that were orbiting around an unseen object. And so you can see these stars orbiting around this just unseen object in the center of the image, and that object is actually the black hole. So the orbits of each one of these stars actually gives you an independent measure of the mass that it's orbiting around. And so each one basically gave you a mass of about 4 million times the mass of the sun. The other great thing is that over a period of 20 years, you can see the instrument upgrade and the resolution actually getting better. So you can see you can actually see the stars being better resolved halfway through this video. Okay, so the thing is that when we look at galaxies like the Milky Way, basically every massive galaxy seems to have one of these supermassive black holes in the center, and it's not clear where they come from. Okay, so how are these galaxies formed? Okay, so the galaxies like the Milky Way, they're formed through something called hierarchical merging. I mean, this is the leading theory as to how galaxies form. JWST, the images from JWST where we're looking at galaxies very early in the universe, some of that data is starting to corroborate that as well. But the idea is that you start with, essentially small clumps early in the universe, and then those clumps kind of merge together to form larger clumps, and those larger clumps form larger clumps, and so on until you end up with galaxies like the Milky Way or elliptical galaxies. Some of these clumps can actually may not actually merge all the way through. They may just end up, as present day kind of really small, tiny clump, small galaxies. You can end up with very large galaxies like the Milky Way, things like that. What differentiates spiral galaxies from others is that, you end up with these larger clumps, but a small clump could pass by it, impart some spin onto it, and so the internal gravity from that object will actually cause it to collapse, but the spin on that cloud will negate some of that gravity, so that's how you can end up with a really thin disk-shaped galaxy like the Milky Way. Okay, so this is just a video kind of showing that whole process, right? So here you start out with very tiny clumps, so you can see that in the center of in the video right there, and eventually these little objects are going to start being attracted to each other by gravity. They'll impart some spin. You can see the gas kind of being transferred to the objects, and eventually what's going to happen is you're going to end up with a spiral galaxy. A galaxy much like the Milky Way. And so you can start to see the arms kind of forming. You can see larger clumps passing by. What's really fantastic is that in this video you can actually see a bar being formed as well. Not quite yet though. But it looks pretty chaotic, but you can see it's still pretty well organized. There's enough rotation in this disk to keep it organized, and you can see the spiral structure forming, so you can start to see arms there. And if you look in the middle, you can kind of see a bar spinning very, very quickly. Oh, now it's a little distorted, but now you can see it. Yeah, there it is. And so you end up with a very large spiral galaxy, much like the Milky Way. Right? So this is hierarchical merging. Okay, so we have galaxies forming, and so what we're seeing here is just a timeline of the universe. So we're here at the far right side. This is the present day. The Big Bang is on the left side. That's 13.5 billion years ago, 13.7 billion years ago. The first stars are here at about 400 million years after the Big Bang. And this is also where we think the first galaxies formed, and this is also where we're starting to see the supermassive black holes as well. So the problem is how are we creating these supermassive black holes so early in the universe? Okay, these supermassive black holes range from millions to billions of times the mass of the sun, and we see them in essentially every massive galaxy in the local universe. So how are these things being formed so quickly, so early in the universe? And that's the problem. We don't know. So the black holes that we know of now, we know that there are stellar mass black holes. So these are black holes that are formed from very massive stars that at the end of their life cycle basically collapse, their cores collapse, and then you end up with a black hole where that star was. They go supernova, you end up with a black hole. And we also have supermassive black holes, and we're not sure how they're formed. And what's weird is that there doesn't seem to be black holes in between these two classes. Okay, so we have supermassive black holes that are millions to billions of times the mass of the sun. We have stellar mass black holes that are, tens to hundreds of times of the mass of the sun. But we don't really see any black holes that are thousands to hundreds of thousands of times the mass of the sun. So there's a missing population there that we don't see. And these may actually be the key to understanding how supermassive black holes form. Okay, so we think that supermassive black holes have to form from something called seeds. Some kind of seed has to get that supermassive black hole going and growing very quickly. Okay, so some of the leading ideas are that you get these supermassive black holes or these seeds directly from the collapse of very, very large gas clouds very early in the universe. I mean, just enormous gas clouds that collapse directly into these seed black holes. It could be the remnants of the first stars. So these stars that are formed basically mostly from purely hydrogen and helium. So these are very massive stars that could collapse into these large black holes that then merge together very quickly into supermassive black holes. It could be just regular stellar mass black holes that just a ton of them form near the center of a galaxy, and then they all just merge together very, very quickly. I think that's a little less probable, only because the time scales are so short that in order to do that, I don't think the time scales actually work out. So the key is maybe trying to find some intermediate mass black holes in the present day universe, in some galaxies, in the centers of some galaxies that exist now. So if we can find intermediate mass black holes that still exist now, these would be very rare objects, but the galaxies that they're in should be different from basically every other galaxy that we see. So if we can find maybe a dozen of these galaxies that harbor intermediate mass black holes, we can see what makes them outliers compared to essentially every other galaxy. You know, are their internal dynamics different? Was their environment different? Things like that. What could have inhibited the growth of these intermediate mass black holes, the supermassive black holes? The problem is that obviously we don't see many of them. So it could be that they simply do not exist. It could be that they grow so rapidly into supermassive black holes that we just don't see them in the present day universe. Or it could be that they're just not easily observed. And we're betting on that they're just not easily observed. If it's the other two, then we won't find them. But if they're not easily observed, then there's a chance we could find them. So we're taking advantage of an interesting relationship between the winding of spiral arms in disk galaxies and the mass of supermassive black holes. So what this plot is showing here is basically the mass of a supermassive black hole in the center of a galaxy on the y-axis. So the 6 is basically 1 million solar masses, the 9 is 1 billion solar masses. And then on the x-axis, this is something called pitch angle. So it's a quantitative measure of the wrapping of these arms. So a low pitch angle means the arms are very tightly wrapped, and a large pitch angle means the arms are very open. And so you can see that when the arms of a spiral galaxy are very tightly wrapped, it corresponds to a high mass supermassive black hole, and if the arms are very open, that corresponds to a low mass supermassive black hole. And so what we think is that if this relationship actually holds, continues downward, if we look for galaxies with very, very open arms, then potentially these might harbor intermediate mass black holes. These could be candidates for intermediate mass black hole galaxies. And so the idea is to try to find these galaxies that may harbor intermediate mass black holes. And the easy thing to do is just look at images of galaxies and measure how tightly wrapped the arms are. And then we could pick out the ones that fit this criteria and then go back with telescope observations and just measure, which takes a lot of telescope time, but what we can do is we can measure the centers of these galaxies, look at the scattering of the stars, and then figure out what the mass of the black hole is in the center. But nobody's going to give you telescope time to just look at every single galaxy, spend hours of time to look at every single galaxy to measure their centers. So we kind of have to cull thousands of galaxies to find the few that are interesting. So the nice thing is because this is all, this can all be done with like photographic data, right? We just need to look at pictures of galaxies and just measure how tightly wrapped the arms are. So obviously there are a lot of surveys, like all sky surveys, right, where basically a telescope, takes a picture of the sky, moves over, takes a picture of the sky, moves over, and so on, right? There are field galaxies all throughout these images. So we just have to pull out those galaxies and just measure how tightly wrapped the arms are in these galaxies. Okay, but the problem is that these sky surveys are not focused on these galaxies, right? So the contrast in these galaxies is very low, right? And so this is an example of one of these field galaxies. So it may actually just look like a weird blob, but there's actually spiral structure in this galaxy. So there's an arm right here, and there's an arm right here. But you can see that the contrast, right? The contrast is so low between the arm and the interarm structure that's pretty hard to kind of pick that out, right? It's really hard for a computer to do that automatically, but people are pretty good at seeing patterns. And so, generally, sometimes when patterns don't exist, but people are good at seeing patterns. And so we thought, well, why don't we have people show us where the arms are? That way we don't have to use these images. We don't have to plug these images directly. When we have people show us where the arms are, we take the tracings that they do of these arms, and then we measure those instead. And so this is the idea. So we basically think, okay, we'll show people a picture of a galaxy. We'll have them trace out the arms. We throw away the image and just measure the arm tracings. and that'll tell us what the pitch angle is for each galaxy. So we ended up building a citizen science project called Spiral Graph, where we did just that, where we showed people pictures of galaxies and just had them trace them out. The issue is that galaxies are not all face-on, right? So galaxies can be edge-on, they can be face-on, they can be at some inclination between. So what we have to do is we have to basically show people the same view of a galaxy, right? And so this is just an example of a 3D printed model of a galaxy somebody gave me sitting on my desk, and I just took different pictures of it, right? So I took it from top down, I took it from edge on, so on. But what you can do is, with some basically Photoshop, what you can do is you can deproject these images, right? You can make them all look like they're face on. And so what you do is you basically trace out the outer structure of the galaxy, and you basically fit an ellipse to it. And if the galaxy is face on, then that ellipse we assume is going to be circular. So all you have to do is just rotate it and then stretch it so it's a circle, and then you have a face on image of this galaxy. And that's basically what we did for thousands of galaxies. So we initially started doing that. We deprojected thousands of galaxies, started showing them to people, but then we realized that the sample that we took from Galaxy Zoo, which is another citizen science project where they classified galaxies basically into ellipticals and spirals, some of them weren't actually spiral galaxies. So we had to take the spiral galaxies from Galaxy Zoo and then ask people, is this really a spiral galaxy? Specifically, we asked, is it a smooth, merging, or otherwise untraceable galaxy, or is it structured and not merging? So structured and not merging means it's basically just a regular spiral galaxy. Smooth, merging, or untraceable basically means it's something else. And so basically, if it's A, for instance, here on the bottom left, this is two galaxies actually merging. This is not a spiral galaxy. B is a really good example of a spiral galaxy. If people pick B, then we had them trace out the arms. And just from that first classification, just kind of that reclassification from Galaxy Zoo, we saw that there wasn't a ton of agreement that every single galaxy was a spiral galaxy. At the bare minimum, there were 51 galaxies out of 6,222 that everybody agreed was not a spiral galaxy. They were either merging, there was some kind of error, it was off center, people were looking at the wrong galaxy, something like that. So at least, that's like 1%. So it's not huge, but there were 51 that were classified by Galaxy Zoo as spiral, but that actually aren't. But we had about 2,500 galaxies out of 6,000 where the agreement was really high. And this is an example of the tracings that we got for these galaxies. So what we did was we had, for each galaxy, we had 15 people basically reclassify it and then trace it. And we aggregated all their tracings and created an aggregate image, as you see here. And what you can see is that in most cases, people agree pretty well. You can see where these spiral arms are. There are some outliers, so you can see there's somebody tracing something way out here. But in most cases, everybody kind of agrees where the spiral structure is. And so what we ended up doing was plugging these images into our software to measure the spiral structure, and we thought, okay, well, we could determine black hole mass from that. The thing is these 6,000 galaxies that we initially picked out were also measured by another team using a different method, an independent method. So the first thing we wanted to do was compare our methods to see if we get the same answer. And what you're seeing in this plot here is kind of the result of that. So on the x-axis is the pitch angles that we measured, and the y-axis is the pitch angles that the other team measured. And the black line is essentially where everything should lie on. Everything should lie exactly on that black line if we measured the same thing exactly the same way. And what you're seeing is that is not the case. And so the problem is that these galaxies don't have a known pitch angle. They don't have a known winding arm, they don't have a known pitch angle. So we don't know who's right. We don't know if they're right, we don't know if we're right, we don't know if we're both wrong, we don't know. So the only thing we can do is try to improve our project, is try to improve our measurements, to see if we're measuring these things accurately or not. And so what we thought was, okay, these galaxies are not necessarily completely symmetric, right? Some of these arms may have a different pitch angle from other arms in the galaxy. These galaxies, some are kind of bunched up on the arms are kind of bunched up on one side and maybe not on the other. They may not be completely symmetric objects. So we thought, okay, why don't we measure each arm individually, measure the pitch angle of those arms, and then recombine that measurement together to come out with a global pitch angle for the galaxy. That ended up being an incredibly hard project. Because it looks really easy to pick out those individual arms just by sight, right? You can see where each arm is, you can see that cluster of lines, just pull out those cluster of lines and then just measure that, right? The issue is doing that automatically with a computer is apparently very tricky. We tried all kinds of different machine learning, nothing would do it accurately. And then my collaborator, my friend Alp, we sat down and he basically figured it out in about a week, 2 weeks. He developed this algorithm where it's basically just comparing lines to each other and then grouping them together. And so how it works is you take the longest tracing in that whole set of tracings from a galaxy, you just blur it out, you kind of make it a little bit fatter, and you take another line, you take another tracing, and then you subtract it from the blurred tracing. And if it fits within a certain percentage, then we say, okay, these two tracings belong together, and we put those in a bin. And then we do it again with another tracing, and we keep doing it and keep doing it. And the ones that fit within a certain percentage, we all bin together, and that becomes a cluster of tracings that form an arm. And the other ones that don't, we go back and we start comparing those to each other, and then we group those into an arm, and so on and so on. And eventually, what ends up happening is you're able to pick out individual arms. And so what you're seeing here is that's the same galaxy right here. So all these arms now are grouped together. So these different colors of the tracings grouped together. And the great thing is, too, it also eliminates these outliers. So you can see this outlier tracing right here that doesn't fit with anything. It's completely eliminated from the arm structure. So now we can go through, take out those arm tracings, and measure each arm individually. But the problem is that it doesn't work 100% of the time. So here are some examples of its failure, where it clearly should have worked. So on the top there, you can see it's clearly a 2-arm spiral galaxy. It was only able to cluster one arm. And then at the bottom, you also see a 2-arm spiral galaxy, but it clustered both arms together as a single structure. So the problem is that we have all these hyperparameters in the background for this arm clustering algorithm that we have to kind of manually adjust in order to get the arm clustering to work. And so, again, now we're back at the same problem. Now we have to look at each one of these images individually and then check to make sure it's right or not. And so what we thought was, well, why don't we just adjust these hyperparameters for a set of galaxies and then have people tell us, does this work or not? And then what we can do is use those results to train an AI to tell us what the hyperparameters should be for a given image. And then it automatically will pick out the right hyperparameters, do the correct clustering, and tell us what the arms are. And so we are now building a citizen science project, called, kind of a spin-off citizen science project from Spiral Graph called Clusterbuster. So this is still a work in progress, but we do have NASA's citizen science seed grant funding to build this, and so we're in the process of building it now. But if you go to this QR code or this website, you can actually go check it out right now. It's active, but it's not completely built, so you can test it out, try it out if you like it. But basically all we do is we show people a clustering image, and you say, does this look right or not? Does it look clustered correctly or not? And in the background, we have a list of all the hyperparameters that created this, and if you say yes, then we know, okay, this is a good image, and if you say no, we also know it's a bad image. And so we can feed that into the AI to tell it, okay, these are the good parameters for an image like this, these are the bad parameters for an image like this. And so eventually, we're going to train up an AI to do this for us. All right. So that's basically it. So Spiral Graph right now is kind of closed down because we ran it through the pandemic. It basically launched during the pandemic, and our first 6,000 galaxies were finished in maybe 1 to 3 months, which was way shorter than we thought it was going to be. We expected it to, I mean, people not to be that interested in it, and it would basically take like a year, maybe a couple of years to go through 6,000 galaxies, 15 people per galaxy. Surprisingly, that ran very quickly. And as we were running out of data, we went through Galaxy Zoo and picked out 14,000 more spiral galaxies that were not measured by anybody. And we got through that in about a year, maybe 2 years. And then we just stopped because we're like, we have too much data. So we put it in pause, and now we've kind of just stopped because now we're working on this other project. So we've shut down Spiralograph for the moment. But once we get ClusterBuster up and running and we get it working, we're going to relaunch Spiralograph because we have there's potentially millions of galaxies that we could do. But in the meantime, so basically, I'm just going to leave this here. What we're trying to do now is basically improve our measurements using ClusterBuster. And if you want to use that QR code, you can go check it out. So thank you.
All right, any questions? Perfect. You want to run that back down?
Hello there. Hi. This is more like an AI question. So when we are actually doing the let the user make the adjustment on if this picture is good, we're basically asking them to sort of labeling these pictures for the AI to use. Have we considered using like generative AI just to generate fake, even possible fake pictures for the AI engine to train itself? That could save time.
Oh, you mean for the ClusterBuster generating fake images?
Yeah.
We haven't actually. We talked about something like that. We haven't actually thought about using generative AI. We've talked about making, just generating our own models.
Yeah.
Just like making really simple toy models on our own to kind of do that. But the problem is that, the tracings that people give us and the galaxies themselves are, every galaxy is a unique snowflake.
Yeah.
Right. So it's hard to like create something that would really work unless you use the actual data. Yeah.
Oh, okay. Yeah. That's probably my follow-up quick question is, galaxies are very unique, and have we determined any physics equations that we can introduce to a physics-inspired neural network or something like that for future AI learning?
Sorry, say that again. So like a physics? Say that again?
Physics-based, physics-inspired neural network for.
Yeah, I mean, to be honest, like, I don't know that much about AI, to be honest. Those really, Alp and Ian are the computer guys on my team. I'm the astronomer trying to reel them in and trying to keep them working on it. But yeah, I don't know. I mean, I'm sure people are working on that. I just don't know. Yeah,
Sounds
sorry.
Good. Thanks.
Yeah.
Any other questions? I got it.
Okay, I guess my question is, would elliptical galaxies be candidates for where these intermediate like black holes could be because they don't have any arms?
Yes, probably. If they're small elliptical galaxies, I mean, so really, you can a good place to look for intermediate mass black holes. So they're candidates in like globular clusters and low mass objects, right? The problem is that in elliptical galaxies, I think you have to find them in like very small galaxies as well. The problem is that that's not really going to tell us anything about how spiral galaxies are forming.
I see.
Right. So I mean I'm interested in galaxy morphology and dynamics, and specifically like spirals and barred spirals, and like how the Milky Way came to be and how we got that black hole and from like this kind of evolution. Yeah, I think with elliptical galaxies, I think you could do it too, but you'd have to do. I mean, you can't do it easily, right? You need to do telescope observations on like low mass ellipticals, which takes time, right? And this could be a very like this method of using existing data and just tracing out an arm and then coming up with a black hole mass is just a really simple, I mean, it should have been a really simple and quick way to look at thousands upon thousands of galaxies, right? And then just picking out the ones that are important. Unfortunately, it's a years-long project now, rather than like, a month. So yeah.
I see, thank you.
That sounds like a new project that you need to start, Leah. Get on it. All right, any other questions?
In terms of that early evidence for like black holes in the middle of our galaxies, you were talking about how with looking at through gamma, where you see those like emitting clouds?
Yeah.
Is the reason why those are able to, because my very basic understanding of black holes is that they should take in everything. Is the reason why those are able to emit in clouds is because of like the high energy plasma, where they're just scattering everywhere, or they're just far enough from the black hole still where they're able to escape?
Yeah, so what's happening is, like the sphere of influence of even a supermassive black hole is pretty tiny compared to the rest of the galaxy.
Okay.
I mean, it's almost non-existent compared to the size of the galaxy. Like that sphere of influence is so small. But the thing is that so much energy can be withdrawn or can be used from that black hole because there's so much gravitational potential energy there that you can get so close to this high mass. That basically you can draw out a lot of energy, right? And so what's happening is this gas that happens to be falling onto the black hole, it heats up because of the friction, and then it creates these charged particles and creates a magnetic field. And when these particles are launched into the magnetic field, and because they have so much energy, they can be launched at nearly the speed of light out of the galaxy. And that's basically what's happening. So it's not directly the black hole. I mean, it is the black hole, but it's not directly the black hole that's causing it. It's the material around it falling onto the black hole. It's given so much energy by the black hole that it just redirects it and launches it. So it's kind of like, it's almost like when they launch like probes and stuff to like Jupiter, they do a slingshot around the sun, or a slingshot around Jupiter. I don't know how satellites really do this, but you've seen Star Trek, right, where they do that, right? So they kind of get really close because they're imparting, because they're basically drawing some energy off of that larger object to kind of slingshot them and gain energy to make them go faster. And that's essentially kind of what's happening here too.
Okay, thank you.
Yeah.
Any other questions?
I wonder if intermediate-sized black holes might be out in empty space in between galaxies, because stellar black holes, they collapse from stars, and overwhelmingly the vast majority of stars are in galaxies. So that's why we see those. And then, supermassive black holes, we don't really know how they formed, so early on in the universe's history, but maybe the supermassive black holes, if they did collapse from just gigantic gas clouds, then, they went on to be just in the center of galaxies, and all these smaller black holes just kind of got left behind, and they're just out in the middle of space.
Well, yeah, that's partially true, because some of these candidates for intermediate mass black holes are in these like globular clusters, right? So these clusters of stars, which are essentially should have been like collapsed gas clouds, right? And so I think there's one example where they think there's an intermediate mass black hole in the center of one of these globular clusters, which would have been a collapse of not a gigantic gas cloud, but a large gas cloud as well. Free floating, I don't know, maybe, but definitely, elsewhere in different parts of galaxies. But, finding them in like near the centers of a galaxy is the goal, because if they're out in the edges, right, that's not gonna be what actually feeds and kind of helps grow a supermassive black hole. But we find them kind of embedded in the center of a galaxy, and they didn't grow. That's interesting. That's why did that happen? What, was there just not enough gas feeding it? Was there not more, more intermediate mass black holes, near them and, merging together? What is the case there? So yeah, that's what we're trying to look for, but in the center, yeah.
Hi, I'm an astrophysics student who is interested in high energy astrophysics, especially in the research field. Where can we look at your research to get additional details and eventually, hopefully, gradually go into your field?
You could look, well, that's a good question. What's the easiest way? I have a website. How about that?
That's great.
Okay,
yeah.
so it's my last name. It's Troy. It's not up there. Okay, so it's Treuthardt. I think it's .github.io. I think that's it. Yeah. I mean, if you look me up, my last name is so rare. If you look up Patrick Treuthardt, you'll find me. And then there's a CV. There's there's links to papers. You can look me up. There's there's the ADS web server that has list papers and things like that. Yeah, you'll find me if you look me up. And yeah, if you find my website, there's all kinds of information there, so you can look up my papers and stuff. So, and my email address is on there too, so if you want to send me a message, you can do that too.
Great.
So
Thank you.
Yep.
Oh, hi.
Hi.
So for this research project, is this something that you're opening up to just citizen astronomers to participate in? Okay.
Yeah.
And if so, what sort of data safety measures do you have in place to protect from bad data? So I have students of 1st through 3rd grade.
Yeah.
So if they want to participate in projects like this or learn a little bit about something like this, or even in the next grade level up, is there some opportunity that they can look at it, learn from it, practice, try it out without maybe causing manipulation in the data by being incorrect, if that makes sense?
Yeah.
They're very bright, but we all make mistakes.
That's a
right?
good question. We haven't for the new project we haven't actually thought about that yet. It's a good question because there's got to be a way to statistically pull that out. Because the problem too is that these hyperparameters there are a lot of hyperparameters and there are going to be a lot of variations that we're trying to plug in, and so this quickly escalates to hundreds of thousands of images. And we can't just rely on one classification per image. It's got to be at least 3, hopefully 5, maybe 10, which escalates the amount of time it's going to take to do this. But yeah, so we need to. That's a good point. We had not come to that point yet where we thought about what would happen if people mess with it. If we only have 3. Yeah, I mean there's going to be a tutorial. There's going to be examples, things like that, but yeah, we need to figure out how to pull out bad data from good data. And so that's going to be something we're going to talk about when I get back. We haven't got to that point yet, but yeah, we need to talk about that too.
Maybe in the test environment.
Yeah, like a demo environment. Well, there's a demo environment, but yeah. But yeah, something like that. We have to figure that out. Yeah. Thank you. Yeah, thanks for pointing that out.
Any last questions?
Would dwarf galaxies be good candidates to find intermediate mass black holes?
Yeah, those are good candidates. But again, that takes telescope time. So yeah, and the thing is too, people are doing really long telescope observations for faint satellite galaxies around larger galaxies. So they're finding all these, when I showed that hierarchical merging, all those little clumps and things like that. People are kind of finding those, I guess, clumps around larger galaxies now too, and potentially maybe those also harbor intermediate mass black holes. But again, it's, you know, it takes a lot of telescope. I mean, you know, just to see those, you know, visually in telescope images takes, you know, I don't know how long, but nights, right? And it's like one galaxy showing, you know, you're seeing a few objects around one galaxy, which is going to take time, and then you got to go back and do spectroscopy on those galaxies, which also takes a lot of time. So yeah, so you're not going to get a ton very quickly. But yeah, so I mean, potentially, yeah, like these low mass objects, these lower mass kind of galaxies are good, should be good candidates. Yeah, for sure. Yeah.
Thank you.
Yep.
I have one more question. So if we're having trouble finding intermediate sized black holes, to what extent is our, I guess, as a whole, as a study, to what extent are we willing to let go of our models of timeline of events and how time works in the formation of stars, so that we're not necessarily begging the question if those are not there to be found?
Yeah, that's a good question. I don't know. I mean, the thing is like, you know, with James Webb, it's pushing back the timeline for when the galaxies are being formed now too. You know, it's like 400 million years after the Big Bang. Like that, I think that's actually being pushed back further, which is screwing with the theorists, right? Because now the theories don't work in that short timeline, so they got to rework the theories to have galaxies build up that quickly, right? But yeah, I mean, but the problem is I think, you know, that early in the universe, they're seeing these supermassive black holes, so they have to have formed somehow, right? But how they form is the question. Like, how can you get something so massive, you know, so quickly, especially when these galaxies are, you know, just being formed. So it's, you know, the whole structure has to be forming so quickly. And then the other interesting thing too is that somehow these black holes scale with structure in a spiral galaxy where essentially there should be no relationship between them. Because again, like the sphere of influence of these supermassive black holes is so small, and the size of the galaxy is like, you know, 100,000 light years across. Like, why is a spiral structure seeing this? I mean, it's probably related to the bulge, which is then related to, you know, the black hole, you know, because that Hubble, you see that Hubble diagram, right? It's probably, you know, a ladder of logic that's scaling up from the black hole outward. But yeah, but it's somehow all of that evolution seems to be happening together at the same time. And why that happens is not really clear. Yeah.
Awesome. Any final questions? Sorry, we're talking about aliens over here. Awesome. Well, can we please thank Patrick once again?